Hello and welcome to this Reigate College Further Maths video on proof by induction. So you know various ways of proving statements. You've done proof by contradiction, direct proof, geometrical proof, and we're going to now learn a new method of proof. So proof by induction, there are 3 or 4 steps. The second step you can count as being 2 steps. You start with the statement, you check that it's true for n equals 1. You then assume it's true for a particular value, and using that assumption, you show that it's true for the next number along, so k plus 1, and then you conclude by induction that the statement is true for all positive integers. It's important that you follow those 4 steps. Think of this as being 2a and 2b all the way through. So if we start with an example, that will make it clear. There's not really very much room in the booklet for this example, so I'm going to work through this on file paper. So the first step is check that it's true for n equals 1. So we're looking here at the sum of the r's from r equals 1 up to n, and we want to show, we're trying to prove that that's equal to a half n plus 1. So we check when n equals 1. Well, when n equals 1, we look at both sides of this equation and check that they're equal. So the left-hand side is the sum of r from r equals 1 up to 1. So that's just 1. It's just adding up 1. The right-hand side, when n equals 1, is going to be a half multiplied by 1 multiplied by 1 plus 1, which is 1, because that's 2, cancels with the half. So you can then put a tick and you write that it's true for n equals 1. So that's the first step. Second step is to assume that the statement is true for n equals k. So we can assume, and use in any further working, that the sum of the r's from r equals 1 to k is equal to a half k plus 1. So we can use this fact now, we're allowed to assume it. We then consider what happens when n equals k plus 1. So when n equals k plus 1, we are looking at the sum of the r's from r equals 1 up to k plus 1. Now, from the work you've done before on series, you'll know that that's the same as saying, let's add up the r's from r equals 1 to k, plus we'd add on the k plus 1 term, which is, in this case, just going to be k plus 1. But now we can use what we've assumed in the step before. We know that this is equal to a half k plus 1. So that's the summation, plus k plus 1. So I've just rewritten this using what I've done before. What I'm trying to do now is I'm trying to get this expression here to look like this expression, but with k plus 1 in place of n. So this is equal to, don't completely multiply everything out, take the k plus 1 out as a factor. So if I take k plus 1 out as a factor, I'm left with, well, I'm going to take the half out as well. So what am I left with inside the bracket? I'm left with k plus, now because I took the half out, I need to put 2 there. Because if I'd taken out k plus 1, I'd be left with 1. And then if I take out a half, I'm left with 2. Now this is, we need to make this very clear, this is a half k plus 1, and then we write it as k plus 1 plus 1 to show that this formula here is the formula we're aiming for, but with k plus 1 in place of n. So if you look, we've got k plus 1 in case of that n, and we've got k plus 1 plus 1 in the place of that expression there. The last step is critical because you will lose lots of marks if you don't put this in. this is the last step, is the induction step. What we've shown here is that if it's true for n equals k, then it's true for n equals k plus 1. So we can write, so if true for n equals k, then true for n equals k plus 1. But in addition to this, we can say it is true for n equals 1. So we now know it's true for n equals 2, 3, 4, 5, 6, or 7, and so on, because if it's true for one value, then it's true for the next value up from that. And so by induction, we get all of the different values. So it's true for n equals 1, and we can say, therefore, you can use 3 dots to be therefore, it's true for all n for all integers, positive integers. So you can write that in set notation if you like. So that's a proof by induction for this first question. 4 steps, or splitting this into 2A and 2B, that you must complete. Let's look at the second question we're given here. So we're asked to prove by induction that the sum of the squares is equal to this. And you've already had this formula, you know this, but if it says prove by induction, then we must use this process we've done. So step 1 is check for n equals 1. So when n equals 1, the left-hand side is going to be the sum of the r squareds from r equals 1 to 1. So that's just 1 squared, which is 1. The right-hand side is going to be 1/6 multiplied by 1, multiplied by 2, multiplied by 3, which is also equal to 1. So it's true for n equals 1. Your next step is to assume that it's true for n equals k. So we assume it's true for n equals k, so that means that the sum of the r squareds from r equals 1 to k, we can always write that as 1/6 k, k plus 1, 2k plus 1. Now we consider what happens when n equals k plus 1. So when n equals k plus 1, we're looking at the sum of r equals 1 up to k plus 1 of r squared. Now that's going to be the sum of the r squareds from r equals 1 up to k plus k plus 1 squared, because that's the extra term that you would have to add on. So we now use what we assumed in the assumption step. So this is going to be equal to 1/6 k, k plus 1, 2k plus 1, plus k plus 1 squared, and that's the expression that we've got. Now what we want to do is we want to make this look like this formula, but with k plus 1 in the place of the n's. We still want to have a 6th outside, so just be careful how you factorize this. Don't make more work for yourself. So we're going to take out a 6th, and we're going to take out a k plus 1. And then what are we left with inside the bracket? We're left with k, 2k plus 1, plus we have to put 6k plus 1 here because we took out a 6th, so we must multiply by 6 to correct that. So that is equal to 1/6 k plus 1, and when I tidy all this up here, I get 2k squared plus 7k plus 6. That's going to factorize, and then we'll work with what we get then. So that is equal to 1/6 k plus 1 k plus 2 times 2k plus 3. So these brackets factorise to give you this bracket here. And that is equal to, wishing I'd left myself a tiny bit more space here, 1/6 k plus 1 plus 1. So remember, we're trying to get this expression, but with k plus 1 in place of the ends. K plus 1. Oh, wait a minute. We've got 1/6 k plus 1. Then we've got k plus 1 plus 1. That's that one. And then we've got 2 times k plus 1 plus an extra 1. So we've got this expression here with k plus 1 in. So make it clear that that's what you've got to. So that's the considering n equals k plus 1. And then we must have our last step, which is the inductive step. So if it's true for n equals k, then true for n equals k plus 1. Statement is true for n equals 1. Therefore, it's true for all n in the positive integers. So there's our proof by induction. The third question on this page, I'll leave you to do that for yourself. It's a similar sort of exercise. It is actually 8A question 2 in the textbook. But you should be able to do this once you've seen these two examples. You can do this third one. So work that one out for yourself.